of ways you might do this. So I think what I picked is to grab the diagonal of this one, and now I know it's upper right corner, and I can get the whole next row from that vanishing point. Now I didn't have to do it that way. I could have just started there and done 4 tiles just like I did the bottom row. And I get exactly the same thing if I do it. You can just see in the picture, there's an enormous number of coincidences when you do that. There's an enormous number of coincidences, and these are the things that allows you to see a perspective drawing and think of it in terms of 2 different perspective drawings of the same thing and reconcile them as the same picture. And there's a quantity, there's something that's making this possible, and you can think of it as the existence of the other diagonals. The other diagonals are all converging at a point on a line. And that is a 4th point on the horizon. Now, what's cool about this is the first tile determined 3 points. 3 points determined 1 tile. Or 3 points, and then once I start, determine a tile. So in fact, that 4th point I get on the line is independent of the choice of tile. That's a consequence of what's called Desargues' theorem. But it means that, and this is the thing I just think is amazing, that if you just start with a line, and a human makes 3 points on the line, because you can dream of a tiled floor, a 4th point is determined. 3 points on a line determine a divine 4th point on the line because we can dream of a tiled floor. So I find that to be an amazing thing, and I find it really unexpected, and this is something else I like to try to convey about math, which I think is more than just that things are regulated, but that we often encounter things that just leave us with a sense of wonder. And that's something, you don't have to think hard to experience wonder, but I think it's good if we go out and label this kind of wonder as a mathematical experience, because it really is, it is mathematical. All right, well, you can go out and do that kind of stuff, but it still doesn't really help us as mathematicians in the world. This picture, I saw this cartoon, this reminded me of something that happened a few years ago. was when my daughter was in elementary school, or middle school, and the person that was in charge of the Newton Public School math curriculum came to town, and there was a meeting. And so I went to that meeting. Now, you don't want to go into a meeting like that going, I'm a mathematician, what do you have to say? So I was kind of trying to hide the fact. But we sat down, and the first thing that happened was they passed out some puzzles. Now, it's really hard to pretend that you're slow at doing a puzzle. It's just, how do you do that, right? They give you the puzzle, and either you're not interacting with it, or you do it really fast, and then you try to pretend you didn't do it, or what. I don't know what I did, but I was outed really fast. Probably I just did the puzzle, put it down, and pulled out my pad of paper, and just went back to working on whatever I was working on before they passed it out. So they pass out the puzzles, and we do all that, and then they talk about about their philosophy of math education. And at that point, I don't know if it's still the case, the kids were teaching children, every number came with a quantity. Every number was 3 apples. Every number was 60 cantaloupes, or 5 oranges, or whatever. Everything had a unit in it. And it was making me kind of crazy, because I'm thinking, little kids are really good at abstraction. They're better than we are. I mean, think about how you play with a little kid. You're just executing patterns over and over. You're not doing this to teach a kid how to bake a cake, even though that's the words to pat a cake. It's a pattern. Kids are really good at abstraction. And I was kind of getting really angry about that. I kept my mouth shut, I think, but probably not. I was kind of annoyed about it. So a couple days later, I'm giving a graduate course on algebraic topology, and I'm doing a unit in category theory, and I'm explaining how fraught the mathematical notion of equals is. and I'm doing this whole bit about, two sets aren't equal. They might be isomorphic, but they're not equal. Like the set that has you as its only element, or that has your father as its only element, and the set that has Darth Vader as its only element aren't equal. They're isomorphic. They're only equal if you're, spoiler alert, Luke Skywalker, or, spoiler alert, Princess Leia. And so I was really going on and on about that, and then I don't know, this is the other thing we do as mathematicians. We scrutinize, and I was thinking about it more, and I'm thinking, those 3 apples and those 3 oranges, those aren't really equal. There's an isomorphism between them. And I'm thinking, wait a minute, maybe they're onto something here. Maybe we're just decategorifying our children too soon. And if we'd really teach them that these 3 apples and oranges are isomorphic, they'd grow up knowing category theory, and they'd have discovered all these knot invariants and everything that you're all talking about here way sooner. So, I don't know. That's what happens when you're in math. And then, of course, the next thing I know, I'm thinking that thought, and then I realize I'm sitting at the dinner table, and my daughter's going, "So, Daddy, what should I do?" And I'm like, hoping I can just know the answer, because that's what we do in math, and not have to ask for the question again. But we just also dig ourselves in those holes somehow. All right. Well, anyway, that's something else we do. But I wanted to sort of go through, so that's what Sally had to say about mathematicians and how we get in there. But there's other people throughout history that this idea of Plato that mathematics was held to some extraordinary elevated standard. It stayed as it stayed as an attitude for many, many years. So here's a quote or a passage from Abraham Lincoln. Maybe it's a little bit too long to read, but I don't know, if you can read this yourself, but he's saying that he wanted to understand when he was studying law what it meant to really demonstrate something. And if you read that through, you'll see that he's turning to Euclid. He goes and studies the books of Euclid to learn what rigorous thinking is and what. Yeah, so this is Lincoln. In fact, he was famously said somewhere else that he never had much formal education, but he had read the 5 books of Euclid. And so in many of Lincoln's writings, you'll hear the language of mathematics in many of his speeches. Here's someone slightly more recent. This is a famous poem of Edna St. Vincent Millay. Euclid alone has looked on beauty bare. And again, I don't really want to read this to you, so I'll just let you read it yourself. But Edna St. Vincent Millay is talking about this sort of extreme, pure vision, this extreme experience of looking at a pure mathematical object. This is a nice poem. Mathematicians didn't really help themselves, I think, over time. I mean, here's Bertrand Russell in 1918 saying mathematics takes us still further from what is human into the region of absolute necessity, to which not only the world, but every possible world must conform. I don't know if we want to claim that much power. And then he goes on to say that mathematics may be defined as a subject in which we never know what we are talking about, nor whether what we are saying is true. So I think we face a different challenge now as mathematicians, and it's probably not great to present ourselves as in control of everything, but hey, we don't really know nothing. In fact, here's a reaction just a couple months ago of Chief Justice John Roberts. I don't want this to sound at all as if it's political, but Justice Roberts is talking about, he's addressing the possibility of using a mathematical formula to make a regulation about districting, and he says he can only describe this as sociological gobbledygook. So again, I think it's probably correct that we don't necessarily want to surrender social agreements to the authority of a mathematical formula, but it's a long ways from Lincoln's view of the role of mathematics. So how did that happen? How did we get there? There's a lot of ways, there's a lot of things, but one I think moment I find really thought-provoking is this famous essay of Wigner on the unreasonable effectiveness of mathematics in the natural sciences. So, as many of you may know, Wigner is a famous physicist that did some very important mathematical work and experienced a situation where there was a mathematical model for explaining certain physical phenomena, and the model predicted a whole bunch of new phenomena, and they were able in labs to go and observe that. So from the title, this always seems like it's going to be kind of a love letter to mathematics, but Wigner is really questioning this relationship of mathematics and its explanatory powers. So the essay is really interesting reading, and I've read it many times, and many times I've been drawn to different parts of it. But let me get to the one where he talks about this. He talks about sort of this phenomenal power of mathematics for explaining natural phenomena. And he says we're in the position similar to that of a person who's provided with a bunch of keys and who, having opened several doors in succession, always hits on the right key on the first or second trial. He becomes skeptical concerning the uniqueness of the coordination between keys and doors. Well, if you read it further, what Wigner is sort of saying is that, is it possible that mathematics is so effective at explaining phenomena because what we label as phenomena suffers from a selection bias? We're only calling phenomena the kind of things that we can use mathematics to explain. So I think it's kind of a matter of faith whether you decide for yourself if phenomena in the universe is regulated or if the made-up idea is that anything at all can happen. But I know my experience in the world is that almost anything I encounter seems regulated at some point. Now maybe it's because I'm a mathematician, but really almost anything you run into, your mind starts to find an explanation or even a theory for it. So let me just, So another thing that I think we're being challenged, in fact, I've been in interviews directly challenged with this question, is this ideal also that goes back to Plato, is that the world should be describable by theory and that these theories should be simple. And that's something I don't know. I think that's something that's probably changing. I mean, we used to think the Greeks held in esteem certain special numbers. And now with computing devices and things like that, you wouldn't think the occurrence of a number, a specific number, was, that you wouldn't, if you did something and all of a sudden pi came up, you wouldn't feel like, I'm on the right track. Pi is an important number. You sort of, we'll deal with any numbers, and the theory, that's somehow not as, well, there's constants of nature, but we don't think about numbers in the same esteem, I think, as the Greeks did. And I suspect the same is true as we start using more computer-aided theorem-proving things. I mean, I guess what I'm suggesting is that our ability to deal with abstract formal systems could be enhanced by having a computer that understands the abstract formal system and that we just use that as an aid. It's like having a board game that has so many rules, no human can know all the rules. We need a computer to tell us the rules, but we're still able to play the game. In fact, in a way, that day is kind of here, and in fact, it's even here in this conference. The methods of higher category theory require really elaborate axiom systems, and if you really want to write down kind of all the details, all the conditions, if you're going to define in fact, this happened to Dan and I once in my office. We were trying to write all the ways Z2 could act on a certain 2 category, and it was just an enormous amount of information that needed to be specified. And it was very recursive, and it was very systematic, and it was something that a computer could have aided us doing. So, yeah, so that's another thing I think, I don't know, I think about in a public talk trying to convey our relationship with rules and with axioms, and that may be something that changes in the future. Okay, well, so somehow I guess I'm speechifying, but I guess this is a speech. But I wanted to say something about this and talk a little bit about the relationship. I mean, we are kind of in an anti-theoretical era. There's AIs that are, and deep learning that are supposed to learn how to do things that won't have a theory. And I wanted to sort of offer you an experience that I find has clarified my thinking a little bit about sort of the presence of data-driven explanations as opposed to theoretical explanations. So I read this article a few years ago called Robopoetics, the Complete Operator's Manual. So this is by someone named Joanna King Slutsky, and you can find the article there. And it talks about, so apparently poets for a long time, since the 1700s, have been trying to find ways to think outside of their kind of habits of forming words. And they've been doing things like taking large volumes and finding ways of randomly selecting words to try to get new poetic ideas. And in fact, I'm just going to push a book that one of my college teachers wrote in the 90s about experiments in computer poetry. So there's a really kind of fun website called Bot or Not. And you go to the website and it gives you poems. And you have to guess if one was written by a human and one was written by a robot. So here's two. One of those, I'm telling you, is written by a human and one by a robot. So take a minute and read them. I'll let you do that. And when you're ready, I don't know, let's take the one on the left. Do you think that's was written by a human or by a computer? How many people think it was written by a human? Okay, and then the one on the right's the one written by a computer? You think that was by a computer or human? Computer, and most people thought that was computer. No. All right, I'm sorry. Everybody gets an A. I'm a terrible grader. I'm sorry. We have really bad grade inflation at Harvard. So that was Gertrude Stein. That was a human. All right, now I have a reason. I'm going to make you do a few more of these, okay? All right, is anybody ready to vote? One of them's computer, one's human. So how many think this is the human one? A few, all right. And how many think that's the computer one? So more thought that's the computer one. And yeah, so that's the computer one, and the one on the right is human. Just bear with me. I just want to do a couple more. So this one's computer or human? What do you think? Computer? Human? This one's really creepy. This is a computer. Isn't that weird? That's really weird. I know. Let's do a couple more. All right. How about the one on the right? Human? Computer? Human? Okay. And how about, how many are voting computer on that one? All right, a lot of people have given up voting. So this is my man Gerard Manley Hopkins, and that one is a computer. That one fooled me at first. I think maybe it's getting tiresome. That's a human. Let's do a shorter one. Is that a computer or a human? How many computer? Almost everybody. So I think the thing I wanted to do, I think I put too many of these up, so I'm just going to skip. If you want, you can go to the website. It's pretty fun. But what happens is you start doing this, and you get better. All of a sudden, you start getting almost all of them. And it's a, what's that?
You guess the opposite of what you really think.
That's one theory, right? That's something you can do. No, you start to notice like certain kinds of rhymes, like the one about the pig rhyming with prig. People don't really say that. I don't know. There's like, but I don't know. What I would hope to do is go through a bunch of these and give you this sense that you're interacting with an AI or with data, and yet you're still having this sense that the repertoire of phenomena is somehow regulated. There's a pattern there. And I think this seems, I don't know, I just wanted to offer this hopeful thought that sort of with this onslaught of data-driven explanations, that it really isn't gonna kind of empty into something totally non-theoretical, that no matter what we interact with, it winds up being something that feels like a theory. There winds up being a mathematical experience in all of these things. Now, I don't remember what else I did here, so I have to do, I think this is the end, but I forget. Yeah. Okay. So, oh, maybe I shouldn't say anything. Wait, don't. I hope this was fun. I hope I goaded some of you into thinking about what it is about math you want to convey. I know a lot of people like to convey sort of our algorithms or convey sort of the path, the reasoning, as I kind of like to convey something about the wonder and things like that. But I think it's really important now that we get out and do that, and that we consciously do that. You know, we're in an era where there's data, there's deep learning, there's all kinds of things in sciences out there, and the math world, I think it's important that we find our own voice and our own way of expressing, of representing ourselves as a fundamental human endeavor that's important and really underlies much of our experience in the world. Okay, thank you.